Science exemplifies the human quest. Science is humanity's premier way of thinking, to harness the world, bettering our way of life, to probe the world, unlocking the secrets of nature. My own quest, on a more micro scale, parallels humanity's quest. How is the world constructed? What is life? What is mind? And while I love learning latest discoveries, I'm always on search for breakthroughs, scientific breakthroughs, those sudden leaps in knowledge and surprising jumps in understanding that change how we see the world and how we make the world. Put simply, breakthroughs change our world. But what characterizes breakthroughs? How do breakthroughs happen? How to explore the nature and process of breakthroughs in science. I focus on the scientific field hosting in recent decades the most breakthroughs, and that's biology. What are scientific breakthroughs in biology? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. The explosive development of the biological sciences has been driven by numerous breakthroughs. From double helix DNA unlocking the genetic code in the 1950s, to messenger RNA coding for a spike protein in COVID-19 vaccines in 2020. The numerous biological breakthroughs make biology an ideal testbed to examine and assess breakthroughs across the sciences. But what distinguishes these kinds of radical breakthroughs in biology from the vast amount of good biomedical science? I begin with a novel way of thinking in biology, complexity and general systems theory. I've come to the Santa Fe Institute in Santa Fe, New Mexico, the cradle of complex adaptive systems. I meet the Institute's past president, a physicist who pioneers how universal scaling laws pervade biology, from the genome to whole organisms and even to ecosystems. Geoffrey West. Geoffrey, how do complex adaptive systems work, and why is that a breakthrough in scientific thinking?
I spent most of my career doing high-energy physics. It's marvelous stuff, but very much in the kind of Newtonian reductionistic tradition, which has been enormously successful and enormously powerful. And built into that was almost unsaid, sometimes even said, that all we need to understand are these fundamental laws, and from that we can build up and understand all the collective phenomena on the planet, in the universe, so that we could understand that somehow all of biology, all of ecology, all of social science somehow will be derivative from the fundamental equations of physics, and culminating in the very phrase, a theory of everything. What was, I think, realized towards the latter part of the 20th century, that this was a misconception, that in the world of biology and social science, the messy world existing on this planet, it has its own laws. And it's mostly embodied, I think, really in the conceptual framework of the theory of evolution and natural selection as manifested by Darwin. And I think that sets the stage for a whole new way of doing science, namely to realize that there are these systems which are historically contingent and are evolving, and they're continually adapting. They're made of enormous numbers of components, and they have emergent phenomena. A city is not the sum of all the people that live in it. Your brain is not the sum of all its neurons. There is an emergent phenomenon beyond that, and that has its own laws. Now, it is indeed a very worthy challenge to ask, can you derive those emergent laws from the underlying dynamics? But nevertheless, I think it's an important and crucial step to recognize that there is a science of these complex systems themselves. And one of the big challenges, I think, of the 21st century is to develop that science. And one of the questions one could ask, is there a science of complexity analogous to the science of thermodynamics, which was the science that grew out of the Industrial Revolution, which seemed very parochial at the time, but turns out that thermodynamics and the concept of entropy is the most fundamental law in the universe. So maybe by thinking of these complex systems and asking similar fundamental questions, we can develop a generic theory of complexity.
And these systems, in general systems theory, apply to the biological world, the social world, the world of technological innovation.
Absolutely. What is remarkable is that despite the fact that these are evolving adaptive systems, they still obey quantitative laws. They still have regularities. And these regularities are a reflection of the mathematical framework of networks and the principles guiding those networks. And I think one of the big challenges is actually to recognize that these laws are not like Newton's laws in the sense that I can calculate anything to any degree of accuracy. And that's the world of physics. And in a way, that's only true of simple systems like the planets or your iPhone. The world of complexity, I don't think there are laws with that kind of precision, but there are laws and they can be mathematized and computational and they can be predictive, but they're statistical in nature.
The science of complex systems and the laws that govern scale in biology and ecology, also in cities and corporations, compose a new kind of science, a breakthrough in category as well as a breakthrough in principles. How do breakthroughs in biology differ from breakthroughs in physics? And can biological breakthroughs catalyze fresh thinking about breakthroughs in general? I consider novel kinds of breakthroughs with a pioneer in the self-organization of complex adaptive systems, a long-term member of the Santa Fe Institute, Stuart Kauffman.
Reductionism stops at the watershed of life. With Newton, you have his three laws of motion, universal gravitation, then you have initial and boundary conditions of, for example, the billiard balls on the table, where the table's the boundary conditions. The table creates the phase space of the system of all possible positions and momenta of the particles or the balls on the table. In physics, you can always prestate the phase space. What you cannot do is prestate the phase space in biological evolution. In biology, there are functions, like the function of the heart is to pump blood. It's not to make heart sounds, and it's not to jiggle water in your pericardial sac. Now, in evolution, new functions come to exist. For example, hearts or flight or feathers that evolved for thermoregulation that were co-opted for flight. These are called Darwinian pre-adaptations. You cannot say ahead of time what the Darwinian pre-adaptations will be. Nobody could have said flight 3 billion years ago, but nobody could have said hearts 3 billion years ago. That means that you cannot state the ever-changing phase space of biological evolution. Therefore, you can write no laws of motion for the ever-changing biological biosphere because you don't know the relevant variables. So a simple way of showing this is consider a fruit fly, Drosophila, and suppose that there is a dominant mutant that arises in the fly. The mutation is a quantum event that maybe changes an A to a U or A to a T or a C to a G, and now the fly has a white eye rather than a red eye. There is such a mutant. Now imagine that the fruit fly is, of course, a classical object, and now it's got a white eye, and suppose that makes it fitter in its environment, and within 20 years there's billions of copies of the single mutant DNA spread around the biosphere. The universe will not make all possible complex things like human hearts. There's a big issue. We made all the possible atoms in the universe that are stable. We won't make all possible complex molecules or hearts. So here's this thing in the universe above the level of atoms, and you cannot explain it by quantum mechanics or classical physics alone. You need the idea of natural selection. And I've already tried to say to you that there's no law that entails the becoming of the biosphere. So there's no law for the becoming of this molecule, DNA molecule, all over the planet.
To claim that there is no Newton-like law for the evolution of the biosphere, that reductionism stops at the watershed of life, is a breakthrough. Not a breakthrough in scientific discovery, but a breakthrough in scientific thought. Is eliminating reductionism in biology a correct conclusion? Suppose it is not. Still, to me, it is a kind of breakthrough. Because the power of reductionism, cutting across all the sciences, pervades scientific explanation, for the good reason of reductionism's explanatory and predictive success. Yet, reductionism is challenged by some, a view that can inform the nature or types of breakthroughs. I know a behavioral neurologist who wrestles with reductionism and its antagonist, holism. He studies patients with strange conditions such as phantom limbs. V.S. Ramachandran.
Some people are just absolutely adamant that reductionism is the only way to proceed, that any complex phenomenon, as a cosmos or a phenomenon you're studying, is best explained by interaction between the parts. Stated in that manner seems very simple. Who could dispute it, right?
Right.
But in terms of actually approaching problems in science, which has been most fruitful, the holistic approach, top-down approach, or bottom-up, looking at the components? And the answer is you need both. To give you an example, a Martian ethologist came down to Earth, and he or she was parthenogenetic, which means that they don't have sex in Mars.
Right.
They divide like amoeba, but they don't have sex.
Right.
Whereas Earthlings, of course, do have sex.
Right.
They come and dissect us, and then they try to figure out all the parts, what they're doing. Then they come across, in one species, like Homo sapiens, there are two varieties. One with these spherical things below, and the other one doesn't. But they're both the same species. You know, why are they two species? Are they one species? What's going on here? Then they watch some things going on, and then this reproduction occurs. But they never will figure out what the whole mechanism is. If they just take the testes and then dissect the testes. So they dissect all parts of the body, dissect the testes, and there's this little wriggling things and parasites in these testes. And what are they doing? They spend years, decades, centuries studying parasites in the testes without understanding what the phenomenon is all about. You need to understand the macroscopic phenomenon of sex, of sexual reproduction, to begin to understand what
the micro is doing.
What the micro is doing.
Yeah.
What the testes are doing.
Right.
What kind of breakthroughs in understanding have you created because you see these very strange phenomena?
By looking at people who have sustained injury to a tiny portion of the brain, noticing that they don't have an across-the-board blunting of all their mental capacity, but often a highly selective loss of one function.
Right.
You can draw conclusions about what that part is doing and how this mechanism gives rise to all your sensory impressions, your love life, your thought processes, your ambitions, your pride. Even though you treasure your life, ultimately just a pack of neurons in your head firing away, right? This is a strange thought if you think about it. And how do you study this organ, the mysterious organ, which is 100 billion nerve cells, firing away and interacting with each other? And where do you even begin? And one approach is to study these patients. And one of the things we studied is phantom limbs. Most scientists, most of us, what we do is bricklaying. We're not great architects.
Right.
We're laying the bricks, but then every now and then we create a great monument, great theory, string theory or natural selection, Darwin's theory. And then suddenly something comes along, a little fact that comes along that obstinately refuses to budge. It says, I don't fit the edifice.
Yeah.
What do? Either you bury it under the carpet or you try to fix it, put a Band-Aid, which sometimes happens, called denial. There's an emotional aspect to it. Let's take the very first one, Copernican revolution. That the Earth is not the center of the cosmos. It's a speck of dust whirling around the sun. Second great breakthrough was the Darwinian revolution. Admit we're a speck of dust, but we're important. We're human beings. No, you're a hairless, neotenous ape. Okay? Then comes Freud, according to his own admission, the third great revolution, which is that all our motives and ambitions and passions and a mind are the result of an unconscious cauldron of motives and emotions pulling you in different directions. Fourth one was, of course, the DNA. Saying we're just a bunch of molecules. My question is, why would people enjoy being diminished? What these great breakthroughs have in common is the fact that they belittle our existence. Why is that? And you can begin to invoke Freud himself to explain this. I think we are all terrified of an annihilation and death and the actual meaninglessness of human life as defined by science. But by doing that, you're saying you have nothing to worry about because you never had any meaning anyway.
Ramachandran recognizes the microscopic power of reductionism, such as in explaining sexual reproduction or human behavior. But he argues that reductionism alone can miss the macroscopic context and meaning, ever analyzing, never understanding. That's why, he says, good science requires both. Reductionism, bottom-up mechanisms, and holism, top-down organization. And breakthroughs in science can occur at both levels. A potent example is how emotion shapes cognition. And I find the neuroscientist whose work on affect, emotion, changes our understanding of how we think, even how we evolve, Antonio Damasio.
It is quite likely that what we call a mind actually begins with affect. That's the very beginning of the process. And in fact, it's quite likely that you can only understand affect in the general framework of homeostasis, and that homeostasis is the fundamental generator of affect. That's what has to come first. And eventually we come to all these marvelous things that we think about when we think about perception, or when we think about reasoning and the manipulation of data from the senses. But the beginning of it is, in fact, with affect. Most of the time, people tend to separate intelligence from affect, as if you could, thinking about intelligence as something rather dry, rather objective, that deals with data, whereas, affect feeling is another kind of thing that is not quite intelligent. And this is exactly the opposite of the reality as I see it, because our intelligence began by being an intelligence of affect. The first signals that allowed us to make good or bad choices, gravitate towards something advantageous for life, or retract from things that were clearly pernicious. That was done with affect. It was done by making the organism feel in an unsettled way or in a satisfied way. And that's what allowed for this polarity, and that's what allowed for a certain intelligent relationship with our surround. It's difficult to imagine that minds could have existed without having a nervous system to permit the development of what we call mental functions. And when you think about nervous systems, we think about something like 500 million years, which is, of course, a pittance, considering the whole period of life on Earth. So prior to the existence of life with a mind to help it, there was the existence of life with a very marvelous governance that could do without mental functions. And yet, interestingly, there was something to help the governance of life during that period, during that long period. And in my view, what helped life be guided during that period is a lot of the functions that end up being expressed eventually in the form of feeling, in the form of affect.
Affect, emotion, feeling is a key driver of cognition, thinking, and perhaps a key catalyst of the evolution of intelligence. That linkage indeed is a breakthrough, but it is a conceptual breakthrough, one that unites two opposing mental faculties, emotion and cognition. While breakthroughs apply naturally to the basic sciences, why limit their scope? Consider breakthroughs in technology. Technology, in a sense, is an extension of biology. When we use technology, we amplify our impact on the environment and on ecology. And with biotechnology and artificial intelligence, our species is accelerating a new kind of human evolution. How do breakthroughs in technology track breakthroughs in physics and biology? I speak with physicist and futurist Michio Kaku.
A breakthrough occurs when there's a paradox, a contradiction between matter. Is matter a wave or is it a particle? That paradox led to the creation of quantum mechanics and atomic physics, the contradiction between particles and waves. But now, today, we have new paradoxes coming because of the advancement of technology, nanotechnology, biotechnology, and artificial intelligence. All the old paradigms are being challenged. We're now beginning to understand why we age And if it's possible to digitally or organically through DNA alter the body, alter our aging process. Artificial intelligence will help because in the future, we will scan the genes of millions of old people to find out the difference between them and locate where aging takes place at the DNA level, and then fix those broken genes. And not only that, but digital immortality may become a possibility. One day we will digitize everything known about Winston Churchill. You'll go to the library and you'll talk to Winston Churchill. A holographic image of him will occur. He has all the mannerisms, all the memories, all the speeches of Winston Churchill, and he's been digitized. And one day, we may be digitized as well. And once we digitize us, where would we go with this technology? I think, and this is a personal point of view, let me stick my neck out, I think we should put it on a laser beam and shoot it throughout the universe. I think that we can take the information of our digitized being, our consciousness, our memories, perhaps in 100 years, put it on a laser beam and shine it to the moon. In 1 second, we'll be on the moon. In 20 minutes, we'll be on Mars. In 6 hours or so, we'll be on Pluto. And we're going to have a laser port on the moon that downloads our genome, downloads all our synaptic memories, and puts us in an avatar, and we become immortal. We can walk on the moon. We can explore Mars, all within the laws of physics.
Regarding uploading ourselves to laser beams and traversing the universe with our consciousness, that's not really us, though.
If you is a biological entity, then yes, this is a tape recorder. But if you is the sum total of everything known about you, the information of your dreams, your hopes, your desires, everything known about you that has been digitized, that is as close as we can possibly mathematically get to the concept of you.
Okay, but the digital you, will that have your current first-person subjective sense of what you feel and are?
This mathematical program will take us as close as mathematically possible to a representation of you, so that when you explore the universe at the speed of light, it is not you, the biological you, but it is as close as mathematically possible, and it is indistinguishable.
But because you are doing it digitally, if you do that once, you can do it twice, and therefore can do an infinite number of times.
That's right. It means that you can explore the universe as a sentient being, that we don't have enough time to, of course, go to all the different planets one by one. But if you make carbon copies, digital carbon copies, then you'd be able to explore the whole galaxy all by yourself.
But they are not related to your original you in terms of an individual. They have
That's as close as Mother Nature can get to a copy of you. Now, is there a law of physics preventing us from creating a molecular replicator that can create anything from nothing? The answer is no. Mother Nature has already created a nanobot which can create something incredible. This replicator can take hamburgers and French fries and in 9 months create a human baby. This is amazing. The greatest molecular assembler ever created is in a female. It rips up every molecule, rearranges the molecules to form DNA, protein, amino acids, and in 9 months, it cries.
To view humanity's grand project of science and scientific discovery, breakthroughs are a lens. What are breakthroughs in biology? The claims are broad. Breakthroughs can be a new way of doing science. Systems comprise vast numbers of elements with emergent properties evolving and adapting. Breakthroughs can be rejection of reductionism at the watershed of life. No Newton-like laws for the evolution of the biosphere. Breakthroughs can require both reductionism, bottom-up mechanisms, and holism, top-down organization. Breakthroughs can be found in the union of opposites. For example, affect, emotion as the basis of cognition, thinking, even of the evolution of intelligence. Technology breakthroughs, biotechnology, artificial intelligence, can lead to radical outcomes, such as features of immortality. To me, a theory or a discovery need not be correct to be a breakthrough, but it should be original, insightful, penetrating, predictive, explanatory, revelatory. Breakthroughs change thinking to be closer to truth.
For complete interviews and for further information, please visit closertotruth.com.